Okay, so in this video we're looking at the 2017 AP Physics Electricity and Magnetism open response question. This is the first one. Up to this point, this is the only one it looks like we can do. So it says answer all of these questions and you get 15 minutes for each question. So we'll try to keep our time here around 15 minutes. I'm going to spend time explaining certain things, which you wouldn't do on the test. But okay, so here we have a very large non-conducting slab, so an insulator, with uniform positive charge density rho naught, and it's fixed with the origin of the XYZ axis at its center, as shown in the figure above. The thickness of the slab is D, the length is L, and the width is W, where L is much, much larger than D, and the width is much, much greater than D. So it's a relatively large slab relative to its height. The large faces of the slab are parallel to the xy plane. Consider a Gaussian cylinder with a cross-sectional area of A and a height h that is positioned with its axis along the z-axis as shown in the figure. So they give us a picture of the Gaussian surface that they choose for us, and then they show the cross-sectional area here. And so part A, we need to draw a single vector on each of the dots below representing the direction of the electric field at the given points. If the electric field at either point is 0, write E equals 0 next to the point. Okay, so point R is above the above the middle of the slab, and then S is below the middle of the slab. And it has a positive volume charge density. Okay, so on this picture here, it looks like we have point R, and this was point S. Point R and point S. Just to make sure here, yep, point R and point S. So if I want to draw the electric field, let's start with point R. This slab here has a positive, so it's got a positive uniform volume charge density rho naught, which means that there are positive, you can think about it as there are positive charges sort of evenly distributed throughout its volume, sort of like this. Okay, and so what you can imagine here, let's just kind of ignore S for this case. So basically whatever we get for R, we can assume would be the opposite for S. So let me just kind of erase S out of this picture here. Okay, and so think about for R, you've got a lot more positives below R than you do above it. Okay, you must have more positives below R than you do. You do have some above R, but not as many. So I'm willing to bet that the electric field must be in the positive Z direction. Okay, the other thing that we can sort of assume, since it's directly in the middle, is and as long as I think we can approximate this as long as we are somewhere in the middle, even if R were somewhere over here instead, I think we could approximate this to be the case either way. But the X, or I guess the Y, since this is the Y direction, the Y component of all of the electric fields contributed by these positives should cancel. So this thing is going to be directly in the Z direction. So if I draw the electric field here, it should be straight up in the Z direction. And then for S, okay, so I'll redraw S, we can just say that S must be the opposite. Okay, so S is just going to be the opposite, just straight down at that point. Okay, so that was it for part A. The electric field is not 0 at either R or S, so we draw the electric field like we did. Part B says use Gauss's law to derive expressions for the following. Express your answers in terms of rho naught, A, D, H, Z, and physical constants as appropriate. Part I says derive an expression for the flux through the Gaussian surface shown. Okay, so we've got a Gaussian surface they give to us, and so we want to find the electric flux through that surface using Gauss's law. Okay, so we're looking at this picture again. And so setting up Gauss's law, we know the electric flux through this thing, electric flux, needs to be equal to the closed surface integral E dot dA, which is equal to, whoops, sorry about that, which is equal to Q inside over epsilon naught. Okay, and so then these are vectors here. So we're just looking for the electric flux, and I like the right side of the equation because it does not involve an integral. So let's just deal with the right side of the equation. So to figure out the amount of charge enclosed in here, notice that the Gaussian surface drawn does not contain all of the charge, so we can't say that Qn is just positive Q. It must be just a portion of it. So if you recall, to figure out the charge, if we know rho, you would take an integral of rho. It'd be a volume integral of rho. Okay, but rho is a constant in this case, and so our total charge here, so this is actually Qn, our total charge Qn is gonna equal the volume charge density, it's constant, rho naught, times the volume, V. Okay, what is the volume of our Gaussian surface? Well, it's the volume of a cylinder, and the volume of a cylinder is going to be the length or the height of the cylinder. So the height here is h, so we'll have rho naught times h times the area of the top part of it or the bottom part of it, which should be the same. So the area would be pi. Well, we'll just say a since the problem says we're allowed to have a in it, I believe. Yes, rho naught a dHz. So you might write all of those things out as you're doing this problem to know that, okay, I'm allowed to have these constants in there. And so Qn just equals rho naught times h times a. And so the electric flux then, if we plug that in for Qn, electric flux is going to equal rho HA divided by epsilon naught. So that is the electric flux through that surface that they gave us. Part 2 says to derive an expression for the magnitude of the electric field as a function of z for any position inside the slab and show that it is equal to E equals rho naught z divided by epsilon naught. Okay, so that's cool. So they give us the answer here, what we should get. We just need to use Gauss's law to figure it out. So I say we just use the surface that they gave us, except for what we need to do. Okay, so looking at this picture here, we don't. So what we want to say then is we want this for any point, either a distance z above or below, right? We want this, so z would be this distance here. Z would be that distance. So we want that for any point z above or below the horizontal. Okay. And so so we've already set up Gauss's law. We have so what would our electric flux be here? So rewriting Gauss's law, we're going to have electric flux is equal to integral closed surface integral E dot dA, and that's equal to Qn over epsilon naught. Qn is going to look very similar. It's going to be rho naught times V again, but what is the volume this time if the height, well, really half the height is Z, right? Above so Z is just going from the 0 mark here and above. So really our height of our cylinder, of our Gaussian cylinder, our height is going to be 2Z. And so what we can do then is use that same equation that we had before, but we are going to replace the h with a 2z. So this is going to become rho naught times 2z times A divided by epsilon naught for the right side of the equation. And then we need to use the left side of the equation to figure out the electric field. So this closed surface integral is going to become a surface integral of the wall of the cylinder, E dot dA. It could be a different E, so for now I'm just going to say E of the wall dA, dot dA I should say. And then we're going to add that to the integral of the top E dot dA, so E of the top E dot dA, plus integral of the bottom E of the bottom dot dA. Okay. All of that is equal to, again, this right side stuff. So let's figure this out really quick. Here's what we do know. From the very first problem, we found that the electric field is basically straight up, and we can say that that's pretty much true until we get towards the edges. Okay, so as long as we stay somewhere within the middle, we can go ahead and say that that is true. And so I think the point of them saying that the width is much greater than D and the length is much greater than D, then basically relative to the height of our slab here, the length and the width are infinitely big compared to it, is what they mean there. And so if that's the case, then the amount of electric field going through, so if I draw my Gaussian surface over here then, right, so here's our cylinder, I guess a cross-sectional area, the electric field is going to be perpendicular to the area vector of the wall of our cylinder, right? So the electric flux going through the wall of the cylinder is 0. And so what we can do, E of the wall dot dA, this is going to be 0. This would be 0. And then the electric flux going through the top has to be, because this is uniform, has to be the same as the electric flux going through the bottom. And so what we're going to end up with is this will equal 2 times the integral of, let's just say the top, for example, E dot dA, which is just going to become 2 E times the area of the top, okay, the area of the top of our cylinder. And then again, we are just setting that equal to, rho naught 2ZA divided by epsilon naught. This area is the same as this area, because that's what we meant when we said, so when we found the right side of the equation, when we took the volume, we had the height times the area. The area is the area of our cylinder, whatever we make it. So these areas are the same, and so they're going to cancel each other out. We can divide both sides by 2. That 2 will cancel with that 2. And what we're left with is electric field is equal to rho naught Z over epsilon naught, which is what we wanted to find. Okay, so let's go look at our problem again. So the next part to this, they say that the charge slab is now placed between 2 large metal plates separated by distance of 0.01 meter, which is approximately the thickness of the slab but does not contact either metal plate. The metal plates are charged, resulting in the surface charge density sigma is equal to plus or minus 2 times 10 to the minus 6 coulombs per meter squared, as shown in the figure above. Assume the charge distribution inside the slab remains the same, so remains unchanged by the presence of the charged plates, and that the slab's volume charge density is rho naught. So on top of there already being an electric field in the slab, there's not going to be an induced electric field from some kind of polarization, which is nice. Okay. What I want you to notice is that, let's say you did not know how to do part 2 of part B. That's okay. You can skip it because they give you some information. They tell you what the electric field is inside the slab, and it's going to be needed for part C. Okay, so if you get stuck, if you feel like you're spending too much time on it, just keep on going and then maybe come back to it because luckily they give you the answer already. So part C, the magnitude of the electric field inside the slab is 0 on the z-axis at a position z naught. Which of the following correctly indicates the value for z naught? Is z naught greater than z equals 0? Is it equal to 0? Or is it less than 0? Justify your answer. And then part 2 says to calculate the value of z naught. So without thinking a whole lot, you're probably going to have to assume that it's not equal to 0. Otherwise, that'd be pointless to have a part 2 to that. Okay, so this might not be completely obvious just looking at it for the first time. So let's think about what needs to be done here. Let me move this down a little bit. All right, so we want to know, basically, qualitatively, where is the electric field going to be 0? Before we could probably say that it's right in the middle based on the symmetry, but is it still at 0? So let's think about this for a minute. Let's pretend that the slab is not put inside the two capacitors quite yet. If it's not put in between the capacitors quite yet, the electric field, so the electric field caused by the two plates here, it's going to point from the positive to the negative plate. So the electric field would point up like this. Okay, and so that electric field is from the plates. So that would be E from the plates. And it's, so as, I don't know if we can make this, so basically as long as we're in the middle, we can make this approximation that the electric field is a constant because of those plates, and it would be equal to sigma over epsilon naught. Obviously in ideal situations, as you get closer to the edges, that's not necessarily true, but as long as we are pretty close to in the middle, that's good enough. Okay. The electric field direction while you are inside the slab, before it's put inside of the two plates, if you recall, if you were above the 0 point, it points up, and if you were below the 0 point, it points down. Okay, so what that means is, let's check out the 0 point here. If I found the electric field at this point, before it was 0 because this electric field would have canceled with that one, but now there's this extra electric field pointing up, and so we would find, if we looked right at z equals 0, we would have a little bit more electric field pointing up. Okay, the net electric field would be pointing up a little bit. And so what that means, if I go higher than z equals 0, then it's going to be even higher. But if I go below, at some point below z equals 0, so hopefully like right around here, the electric field inside of the slab should cancel out the electric field caused by the plates. Okay, and so qualitatively, we can say that z naught is going to be less than 0. It has to be less than 0 to cancel out. So for part C, z naught would be less than 0, and the reason would be, so if we write a reason here, below z equals 0, the electric field, the E field inside the slab points down. I spelled points wrong. Points down. Points down, while the electric field from the plates, so E plates, points up, so they would cancel. And I think if you draw a picture, that would also help the reader too, kind of like I did. All right, so then the last part to here, or I guess not the last part, part 2 of part C, we want to calculate Z naught, okay? So to calculate Z naught, what we want to do to calculate Z naught is we want to know some kind of equation that represents the net electric field in between the plates, set it equal to 0, and then solve for Z, okay? So E net, so let's think about this for a minute. The net electric field, so E net is going to equal, so we definitely have this electric field from the plates pointing up, and so we'll have E from the plates, and then we're going to have to add that to the electric field from the slab. Okay, and luckily we know both of these things. So E from the plates is going to be sigma over epsilon naught, and we're going to add that to the electric field from the slab. We found that earlier. Let's go find that. That's rho naught Z over epsilon naught, where they give us that. So if you didn't know that, you could just use what they give you. So we have rho naught Z over epsilon naught. Okay, just to kind of think about this for a minute, as long as Z is positive, then the electric field from the slab is pointing up, and so we can keep this, so you would add these two, and then if Z is negative, it would point down, and that's what you want. You want those to subtract each other. So this looks good, the total electric field. This equation should represent the total electric field. We want to know where is it 0, so we're going to let E equal 0 and then solve for Z. So E equals 0, we'll have sigma over epsilon naught plus rho naught times Z over epsilon naught. So we just need to solve for Z. So we'd have rho naught Z over epsilon naught equals a negative sigma over epsilon naught. Multiply both sides by epsilon naught, divide both sides by rho naught, and you get Z is equal to negative sigma. The epsilon naughts cancel out, so you have negative sigma divided by rho naught. And if you plug your numbers in, you should get negative 0.002. Or negative, so in my calculator I get negative 2 times 10 to the minus 3 meters, which is equal to negative 0.002 meters, so 2 millimeters. Okay, so that was that's all for part C. Part D says to calculate the magnitude of the electric potential difference from the center of the slab to the top of the slab. So we want to go from from the center here, we want to know what is the difference in potential here. So what is delta V for this? Okay. We know the electric field in that region. We just kind of set up an equation for it. And so delta V, let's use a different color for this last part. So delta V, equation for delta V, we have negative integral from point B to point A, E dot dr. Okay, we are going from, so negative integral, we're going from 0 to the top of our plate. So I'm just going to say Z top, and we will plug that in later on. Z top is going to be all the way up to, well, it'd be half of this, so Z top, I'm just going to write that now, Z top is going to be half of the total distance, so that would be 0.005 meter. Okay, so then electric field, we found this just a second ago. It's sigma over epsilon naught, so we have a sigma over epsilon naught plus a rho naught Z over epsilon naught. And dr, since we're integrating, it looks like with respect to z, that's our only variable here, dr becomes dz. Okay, and then we're just going to do our integral. So this would be negative, the integral of sigma epsilon naught is going to be z sigma over epsilon naught. I'm going to put the negative in a, I'm going to put this up in a parentheses. So we have negative and then z sigma over epsilon naught, and then we're going to have plus, it looks like rho naught z squared over 2 epsilon naught would be that integral. And then we evaluate this going from z equals 0 to z top, which is 5 millimeters. And so delta V then, delta V is going to equal, so we would have a negative, you'd have z top times sigma divided by epsilon naught plus, and you'd have rho naught z top squared over 2 epsilon naught, and then minus, z is 0 for this next one, so you would get 0 plus, and then z again is 0, so you just get 0 for everything. Well, it'd be minus and negative. It doesn't matter. It's 0. Okay, plugging in our numbers. I'm not going to plug them in on here, but plugging in our numbers, you plug that into your calculator, you should get a negative 2.5 times 10 to the third volts. That is part D. Negative 2.5 times 10 to the third volts.